Okay, this is Mark Anderson. I'm just about ready to begin my presentation on 40 DOEs in 40 minutes. My background is chemical engineering. I've been working in DOE space for over 50 years, starting as a summer engineer at General Mills Specialty Chemical. And I started doing my first design of experiments with no knowledge of design of experiments or statistics. But luckily, I had good mentors at General Mills with their heritage from the development of stats in fields of agriculture and then migrating into the chemical industry. So it's been a great career for me. I've also done some work in management as a master in business administration, but I've come full circle at this point as engineering consultant with Staties, working at about a 60% rate to kind of pay back and help people apply these tools of DOE for their own benefit. And so that's been my mission in recent years. Now, this is an impossible mission that I was given by our marketing director, Rachel, who's promoting the fact that we're 40 years now as a corporation at Staties. Although we go back even further than that, doing business in the state of Minnesota, but this made a nice little hook to talk about 40 years and to make a theme of 40. And so she said, Mark, how about if you do 40 DOEs in 40 minutes? And I kind of hemmed and hawed and didn't really agree with it. But finally, I decided I would embrace this challenge. And so here we are. So let's see what we can do with this. We'll do our best. Okay, so again, welcome everyone. You're on mute. Um, I would ask that if you have any questions that you send those to me at the Mark at Staddy's personal address, rather than trying to bring them up during the presentation. There just isn't enough time, particularly on this one. And also, this will give you more to work with to think about your question and give me time to think about a good answer to it. So if you have any questions along the way or comments, make a note and then circle back, after the presentation. Similarly, for those of you that are watching this on YouTube, it'll be recorded later. You may have some questions. You could address those to me if I'm even still around by the time a person gets to it on YouTube, or you could address questions to Scatty's, the general address. But for this live presentation, get right back to me. I'd love to hear from you. Now, presentation slides are going to be posted to the site along with that link to the YouTube video. And I've made a note here, and I've used this little pause button to try to help me deal with the large amount of material that I've got here by necessity. And so I would suggest that you go back to the website, find those presentation slides, and then later, if you want to read through some of the abstracts, if you're not able to read them fast enough, you'll have a chance to do so. It's just going to be too time consuming for me to read through every abstract. So let's watch for this pause symbol, and that'll be a cue for me to just leave you a little time to read. I'll try to read through it to try to get a pace, and it's going to be a little bit too fast. So then again, go back to the presentation slides to review, all these different abstracts that I'm going to present. Okay, so if you're still with me, press that raise hand again. All right, and Andrew, thank you for that. Darren and the feedback. We've got a nice little group here today. I appreciate your attendance. Okay, so let's start. So again, my mission is to try to talk about 40 different case studies within 40 minutes. You can read, what my mission is here in quotes. All right, so you see that mission I've got. Now, the full disclosure, I'm no Ethan Hunt, who's the Mission Impossible character played by Tom Cruise. So, though it's fun to focus on the 40th and make a cute little connection of 40 DOEs in 40 minutes, the time frame, I don't think I'm going to make it. And maybe I would get half credit by covering the 40 DOEs, even if I don't quite make it within 40 minutes. I really don't know how this is going to go. I wanted to do a couple of in-depth demos along the way. Otherwise, it would be totally boring just to bring up, the title of the DOE case study and the abstract. So every once in a while, trying to throw some hot spice in, by talking about, the actual data and doing a demo. So that's my idea, but I've never done this before, so it's a whole new enterprise. So here's where it kind of stems from, curated and by our market development manager Rachel, and hats off to her for looking through this and coming up with 40 that were fairly interesting. But you have a chance to go back not only to look at my slides at the site I showed you earlier, but at our main website for Staties, find a publications option, and there's a searchable field that says industry. So what I did was, for each of the DOEs I'm presenting, I put down the industry category, so you could actually go back to this site and dial up the industry and kind of search through and find the particular case study that I'm talking about, and you'd find a nice little write-up that was done. These were beginning probably in the 1990s, when I recognized as the general manager of Staties, being in charge of the marketing and doing everything, that it would be useful to promote our users to write up their experiences. It'd be helpful for them, feather in their cap, good for their company to get the publicity, and then good for Staties. So a whole series of case studies were developed over a period of time. And every once in a while, there'll be a case study. I'd like to see more of them, and that'll be something I'll ask you all to consider, is writing up your own story. But we have quite a repository there at that case study site. So we begin with number one, which is going to be under the category of factorial designs. And this one features injection molding, which is a very common application for factorial design because it's easy to make the changes to the different process factors. And there's a lot of issues to contend with, in particular shrinkage. And so this study details how manufacturing engineers at an injection molding company set aside two lines, and then they blocked on those lines, which is a very important tool. And they ran a quarter fraction study of 7 factors in 32 runs. And they were able to uncover interactions that revealed that by reducing moisture and going to longer cycle time, they could make their process robust, that is, the shrinkage more consistent, against the variations in booster pressure. So this one I read through for you, even though I've got the little pause button, but I'm excited about this particular study. It was a good, really good one. By the way, if you go to the website, you'll see the article. The reporting rates is as high as 20%, which is not right. Those rates were multiplied by 10, but they weren't noted in the post, so that's another disclosure. I'm going to show you a design and a model that's going to be slightly different than that published in my demonstration. So what I'm going to do is I'll tab over. Let's escape out of this, I think, to begin with. All right, and so now we're back to the main PowerPoint. Go back to my desktop, which is astronomy picture of the day. It looks like some sort of eclipse, so I'll have to take a look at the explanation of that later. And then I'm going to run a program called Staties 360. And this is our flagship program that has the additional tools above and beyond Design Expert of a Python script editor to make the 360 vision and view of bringing in apps from the Python world. There's also a couple other little bells and whistles, but essentially it's Design Expert slightly supercharged. So that's what I'm going to be showing, and this happens to be the release version from last October. We are going to come out with a new version here any time now, within the next few weeks, hopefully, or next few months. We'll come out with a new version of Staties 360 and Design Expert. So what I'm going to do is I'm going to open up this file called inject. And you can see I was actually working with the beta version when I created this. So I'm going to press OK. That allows it to be opened in prior version. Um, and then I'm going to rebuild this. But before I do, I'm just going to ping and ask if you're able to see this layout that shows the factors of mold temperature, cycle time, etc. And to the right, I'll show you the response. Okay. And so now you have the drill, and Alan is putting his hand up. And so, Darren, and I've got enough of a sample size now to tell me that this is probably working. Okay, so now off to the right is the response for shrinkage, but I want to show you how this was built. For those of you that are less familiar with the software or maybe watching this on video and have never used our software, it starts off with this design builder that has the white diagonal of full factorials, and then we have various fractions, and these are color coded like a stoplight. The green are go ahead high resolution to characterize interactions. Yellow are more for screening, but they can give you some information on interactions. And then the red are more like kicking the machine to see if it still works, applying environmental variables like temperature, humidity, and do what's called a ruggedness test. These I don't recommend for screening or characterization, but only for the final testing. Now, in this case, they went with a yellow design, but it's a higher fraction of a yellow design. And then they broke it into two blocks. And you can see some of the smaller designs are unable to be divided even into two blocks, and so they get grayed out. And normally I would like to do center points, which are midpoint levels of the factors, but oftentimes for screening, you're in a hurry, so you don't do those. But for characterization, I'd recommend the center points. Then there's information about the alias structures. And now we type in this case, the 7 factors, units of measure, the types, which are all numeric, but they could be categoric, like supplier X versus supplier Y. But these are all numeric. And then here are the 2 lines that we blocked the set aside manufacturing to. And our main goal here is just shrinkage. And normally I would do a little power calculation. In this case, the experiment's already done, but we want to be careful that we don't cut it back too far. And we want to be able to see that the difference we're trying to detect, given the noise that we have in our system, with that in mind, we have a good chance of seeing what's important. That's a whole nother topic of power that you might want to look into. With trying to do 40, I'm not able to spend as much time as I would like to. And so I'm just going to go ahead then and reopen the file. And then without spending a lot of time on this, normally I would do some scatter plotting just to see what some of the main effects are. And just quickly here, I'm seeing that cycle time, as you increase it, seems to reduce the shrinkage. And now we go through a fairly quick selection using graphical tools of the effects that stand out on this half normal plot, and then we see it emerge on the Pareto chart above these t-values and corrected t-value limits. So this looks very promising that we've got the vital few main effects and 2-factor interactions. We've got a whole pile of trivial many that are going to be used for error estimation in our analysis of variance. And now we focus on the p-values. We see very significant results overall, and for the individual effects that we've chosen, really good predicted R-squared and so forth. And then we would look at the diagnostics. And my diagnostics that I'm focusing on are the normal plot of residuals, residual versus run, which is like a control chart, and then the box-Cox plot, which is very important. And we notice that we can get some improvement on this by taking a square root transformation. So seeing that, I would then set up a new analysis, and following the advice of box-Cox, do a second run on this in square root. And I think what happens in this case is we get a very similar outcome, but maybe a little cleaner separation of the vital few from the trivial many. Yeah, we know there's alias terms in here, so we have to be a little careful about these 2 terms. Let's assume that since they involve the parents of B, C, and D, that the guess of the program that it's B, C, and CD is probably correct. However, we would have to normally keep in mind that these two-factor interactions are alias with other interactions, in particular the BC interaction, and do some confirmation. But assume that this is correct, and we were able to guess correctly at what those interactions are. Okay, I don't really see much of an advantage in terms of the normal plot, but we're in the zone for the Box-Cox. So I would do it in this scale. And what this is going to do is show wider, least significant difference bars for higher shrinkage results, which is probably correct. As the shrinkage goes down, the variation in the shrinkage has to be reduced because we're getting near to zero shrinkage. So I think this is going to give you a more accurate interaction plot. Now, what's interesting here, and I left myself some notes that I would flip this BC interaction plot. So rather than putting cycle time on the bottom, I'm going to put the booster pressure on the bottom. And what this does is it shows you a nice flat red line where we're getting a robust operating condition by going to the long cycle time. So that's one of the key interactions. The other one is this interaction of C and D. And this one is showing that we get a robust operating condition to the booster pressure by going to the low moisture. So in the end, we can use these graphs to come up with conditions, as I mentioned here, where we can develop a very consistent shrinkage, which is really our goal, by reducing moisture and going to the longer cycle time. Now, of course, that's going to cost a little bit more, but I would say mission accomplished as far as the injection molding is concerned. So there's a quick deep dive into one of the 40 that I have, and you can expect that I'm going to have to now move pretty quickly ahead. And so, but I'm going to ping just in case here, and see if you guys are impressed by the idea of using a two-level design to reveal interactions and try to find robust operating conditions. Yes, is that desirable? Yes, yes, yes. Okay, good. Just checking, making sure that you're paying attention. Okay, now here are some others. And what we're going to see as we go through this list of others is that we have a publication, and you can go to our website and look under, for example, the industry manufacturing, and you would find this machine design article for the software sleuth solves engineering problems, and then see that this relates to an aluminum casting process. And just, kind of read through that. The thing that strikes me here is oftentimes the story, one factor at a time, has been applied, and then they finally decide they better do a multi-factor approach, is kind of a common theme. But all of these have got, some success story. In this case, the defect rate from occlusions is reduced to zero. All right, now here comes another one in a completely different field. I worked with this Pete K. Batterjee, and we gave a talk at ASCHE conference in 1998. He was actually working here where I'm currently located in Florida at my winter home at a phosphate mine, and they were producing fertilizer products. And so he was able to do some work with a full factorial and four factors to maximize nitrogen content, which made it less susceptible to impurities. So if you're interested in that, follow up as I've suggested. Okay, now we turn our attention to a completely different industry, paint and coatings. There's actually a number of these paint and coatings because this journal published a number of DOE case studies, including this one on hot ink roller impressions by Jennifer Borkovich and Lisa Surowitz. They did a 16-run DOE, and they felt that the cost of that was recovered within 1 month because of the resulting improvements. And they were able to achieve a 1/3 increase while decreasing variability, which is a common theme, nearly threefold. So that's pretty cool. All right. Now we're shifting from a process industry into a hard good industry, which is a little bit unusual in building a medical cooler. The process industries thrive on the multi-factor testing because they can easily change the levels. But operations that are making hard good like a refrigerator have a little bit more work to do, but nevertheless, a multi-factor approach certainly is merited. In this case, it was a workshop student, and so they went back and they looked at three factors, and they saved 18,000 just from the testing being more efficient, and then 70,000 by streamlining their equipment. Pretty cool. All right, now we shift our focus to renewable energy. And this NREL applied a five-factor DOE for solar air heaters. Now, this is actually another manufacturing situation. So we've got a couple of those in a row, which is very exciting. And they were able to look at many combinations of things very quickly and develop some better outcomes, in terms of renewable energy. Okay, now packaging. And this happens to be for this body wash, okay, in a polyethylene terephthalate bottle with a polypropylene dispensing closure. And they were having trouble with it. It was leaking. And so they did a multi-factor experiment. They solved the problem and saved over 100,000 at Mary Kay. Very cool. So now back to paint and coatings. Weatherable hard coats. This one I'll just lead you read because there's a lot of words here, but you'll see some good things. Florida again. And then the last bit of it, they won the best paper award. Yay. This is a 3D plot showing levels that are treated categorically and the responses, two of them, which were microcracking and adhesion. So that's kind of a neat graph, and it shows, much higher hours of exposure that they were able to withstand. All right, continuing on with paint and coatings. We have this experiment, which I'm not real familiar with, that involves a Tabor test to improve this plasma coating process. And so take a look at this. I'm just kind of highlighting some of the things I see here. Of course, I always like to see the word about interactions, Oh, this one, notice that they did a fold over. So they first did a lower resolution experiment. Actually, as it turned out, it was a resolution 3 design, which I don't normally recommend. But after they folded it over with all the complete opposite levels, they made it into a resolution 4. So in the end, it was okay. And then they were able to do some further work, even with the resolution 4. The interactions are alias, but eventually they were able to get to the bottom of it and develop precise control of thickness and other attributes that were critical to quality. So that was nice. Now shifting over to semiconductor industry. Half fraction, oftentimes people are running these fractions to try to save the number of runs. This was a Six Sigma project, and they were able to increase production of these printed circuit boards by 25% and do it, at a higher quality level, reducing solder opens and shorts. Very good. Okay, now we get to another featured DOE, and I'm definitely not going to make the 40 minutes. I can see that already, but hopefully you'll bear with me on this. But I do have 40 DOEs, and I've lost track of how many I've covered so far, but there's quite a few we've gotten into that are in the factorial section. This one involved an automated assay optimizer, and it was actually from Beckman Coulter, and we were doing quite a bit of work with them. And our consultant Sherry worked with two of their people, and Lisa, on this little project. And so they did this full 2 factorial. They were looking for very small differences. So to develop power, they replicated this design of 8 runs 5 times. That makes it 40, but there are 96 wells in a plate. And so that still have plenty of opportunity for them. But 5 was enough, and with the robot pipetting, it was easy to do, program it in and get her done. And they discovered a significant interaction leading to maximization of the fluorescent signal. So this one I've got. So I'm going to close this out. And I'm going to open this assay. And again, I created this in a beta version of 24, which is okay. I can look at this in the production version of 23. All right. Now, it's been a while since I've asked, but do you see this experiment with cell number, stimulant, substrate, fluorescent units? Yes, yes, yes. Okay, perfect. Okay. Now, this one, we're trying to optimize or increase the fluorescent output of this, or maximum fluorescent intensity. Sometimes they call it MFI. And now the design itself is a 3-factor full factorial, but in order to get enough power, we needed to replicate this. So they were looking for a difference of 400, but the standard deviation was 400. So with 5, you get above the 80% we recommend. But if we were to try to go back and just run 2, let's say, you'll see that the power would drop off and we wouldn't be able to detect the 400 given the noise of 400. The probability would drop below 50%. That would be bad. So this is an example of application of power. We actually use this in our class for modern DOE, this particular example, to get people thinking about powering up their experiment or being careful not to oversize their experiment. And that's mainly what I wanted to show. The advantage of replication also comes into play in our half normal plot. We show the pure air that's developed with these little Christmas trees, which are these green triangles. And so embedded in all this degree of freedom we get for pure air from the replication, there's 32 degrees of freedom because you get 4 for every group of 5, are some effects that were not significant. So really it was this biggest effect of stimulant obviously is going to help, but then the interaction. Another aspect of this study is when we press forward, it warns you that the model is not hierarchical, and that's an ill-formulated polynomial model if you don't have the parents of the higher order terms. So substrate actually comes into play because of that, but it's also pretty close to being somewhat significant. I think it falls a little bit above 0.05 at 0.07, but it needs to be there as part of the family. Another thing that I can point out on this one is that there's fairly low adjusted and predicted R-squared, but that just means there's a lot of variation because of the natural process of the biology. But by doing 5 replicates, we're able to cut through all that variation and develop a strong view of the fact that the stimulant and substrate in combination thereof do affect the response, but there's just a lot of other things involved. And from there, you could go on and work out, what the optimum would be for these 3 ingredients. And the cell number actually drops out entirely, which is a little bit surprising. And we could use our optimizer with a stretch target at the upper end. And we could say we want to get at least, let's say, 3,000, or else the experiment is not a success. And then it'll point out a combination of things in theory. Let's make this 2,000. Okay, so I tried to put the minimum up a little bit too high because actually it's predicting the best we can do is 2,800. We observed 3333, but there's a lot of variation, in these fluorescent unit measurements, and so that was just a kind of a result due to variability that was higher than what we probably should expect overall on average. All right, so always interesting things that are happening, and I love looking at data. So anybody that's a user wants a second opinion, feel free to send in what you've got, to our stat help group. And there's an address. If you go to the website and look under the support icon, you'll be able to see, how you can get that into our group. And so that's a service for our users. All right, still more. 3 more pages of factorial design. So what's next here? How about paper industry? An unexpected interaction with a new blue dye. And so they understood better, how to manage that dye with a full 2-level factorial and 4 factors. So you can go back and read more about that in this article called Design of Experimental Training Banishes Purple Paper Blues. That's interesting. Okay, then we get over to a welding operation. And this welding operation was trying to get this bolt mounted on, and it was kind of tricky trying to get that done. So David Gore was working on this along with his colleague Donald Langston, and they used a full 2-level factorial plus 4 center points. So that was good to check curvature. And they were able to tackle this welding process that was unacceptable. And they were able to get that unacceptable level eliminated, essentially, and do it at cycle times that maintain the desired rate of manufacturing throughput. Very nice. Herbicides, or do we say herbicides? I'm never quite sure. I think it's herbicides. Were investigated in a pilot to production scale-up process, and they were having trouble with clogging on these sprayers. But they were able to work it out at the pilot plant, but at full scale, it wasn't really going like they expected. So they went to the full scale level with a multi-factor approach, and they were able to solve the problem and save a potential loss of millions of dollars of business. So that was quite impressive. Now back to the process industries with adhesives and sealants, trying to make a tape work better. It was failing intermittently, creating a lot of scrap and downtime. Here's again the theme of using the 1 factor at a time, not getting anywhere with it. Finally, they realized that a multi-factor approach might be the way to go because there could be interactions, and it's much quicker using that for main effect estimates as well. And so they're able to maintain full production without any change in the formulations. Awesome. Another process industry example, but this was actually a measurement that was being developed by Ron Stites. And so he was able to validate high pressure liquid chromatography measurement method to do the assay on ethanol and do this over a wide range of operating conditions. So that was another interesting application of factorial design, in this case for method development and validation. Now we get into something that's a little bit more complicated. I had a look at some of the chemistry here of what a peptide bond is, but evidently the increase in yield on this peptide bond was very dramatic and very important for life-saving pharmaceuticals. So 2-level factorial design again, comes out. All right, now we've got a little angle coming in here on this case study because it's what's called a split plot. And I've got a picture of an agricultural split plot laid out here where the whole plot has 3 subplots of corn, potato, and starch. And then they apply 1 herbicide to it from the airplane crop duster, and then they go to the next whole plot with a different randomized plan of corn, potato, and squash, and it goes on like that. Now, early on, this was before I think some of the tools that we developed that are included in our software, Julia O'Neill worked with a split plot to avoid taking over an hour to empty out and clean an entire coding system for each formula. By using the split plot and identifying hard to change factors, Um, they were able to vary some things that were easy to change and work those within the hard to change groups, which are called the whole plots. So the formulation itself was the hard to change. So they would kind of batch together the formulation with the varying amount of catalyst, additive, and the coarseness of the particles, right? They would put that into the line and then they would vary randomly across two levels of time and temperature within that, and then switch to a different batch. This reduced run times to 15 minutes, so it was a huge advantage. And then furthermore, they applied a fractional factor that reduced the time. So the combination really worked. There is a price to pay in terms of your ability to test the significance of the hard to change factors. But it worked out very well for Julia and her team. They were able to reveal the causes for visual defects. And because they were doing it at full scale in a rented customer line, it was really vital that they reduce the amount of time. So a really nice application of split plots. Here's another one, and this one is going back to the 96 well plates. But the difference of this is that before they pipetted the stuff into the cells, they first treated in a thermocycler with two different times and a temperature. These are basically process factors that are hard to change. So they would do that in one combination of 8 possible, and then they would randomly pipette in 6 different ingredients into the 96 well plates. Now, if they did a completely randomized plan, they would have to do one plate for every one of the 256 combinations that we have in this 1/2 fraction. Um, but by doing it in groups, they got it done within 8 96 well plates. So divide 256 by 8. If you've got a calculator in front of you, I think it'll come out 32. 32 times more efficient to do this grouping and apply as hard to change in a split plot the thermocycler factors. And then within each uh, group, you then have subplots, which are actually subplate, and the whole plot are the whole plates. So there's an interesting correlation in this particular case of plate and plot. So I always enjoy that, being a person that likes playing with words. Now I'm already coming up on 38 minutes, so I can see that this impossible mission is starting to bite me a little bit here. So we got to keep moving then into response service designs, and I don't think I'm going to be able to do as much demoing as I would have liked here along the way. So just bear with me here on RSM, which is an optimization tool that involves at least 3 levels of each factor. Here's one in the semiconductor industry. And what's interesting here is that they've blocked off a region of these 2 factors and created what's called a multilinear constraint. I sometimes call it a multi-factor constraint. And this is a very important tool that you can apply, and then you use an optimal design to populate points. Typically, you get the extreme vertices, overall centroid, you try to get some edges, but the program has an optimal algorithm that'll fill in, the gaps. Well, that worked really well to minimize the average delivery time for the transport of these wafers. Apparently, there's little containers that go on rails and move these wafers around. I've never seen it, but it sounds pretty fascinating. So check into that if you're interested. Now, this is one that's timely with getting our 2 astronauts finally down from the space station and splashing off here not too far from where I live outside of Tampa. And they were able to get them down and get them out yesterday. But of course, the big issue is the tiles that are keeping them from getting burnt up. And if you saw the pictures in the news yesterday, they had beautiful sear marks around the capsule. So it held up really well. But there were times when those tiles did not work so well on the space shuttle, for example. And so this study that was done by Richard DeLoach they used screening experiments, reduced the number of factors from 10 to 7. And then this was actually done in a simulator. They applied optimal design to provide useful models. And they were able to quantify the impact of the geometry of the tiles, on these thermal and structural loads that would cause failure. Interesting application: design and analysis of computer experiments, or DACE is the acronym. Design and analysis of computer experiments. I've seen that. And we have tools in Statis 360, notably Gaussian process modeling. And we also have designs that are space filling, Latin hypercube, and optimal space filling, if the results are deterministic. Um, on the other hand, if you apply normal tools, you can develop what's called a transfer function, which is a polynomial model. And I've seen this done very successfully, for example, on designing power and jet turbines at General Electric. So that might be something to look into if you're working with simulations. All right, now this was a case study applying response surface methods to starch nanoparticles. And they use a central composite design, which is the core factorial for two factors forms a square, center point, which you would replicate a number of times to get power in the middle, and then putting points outside of the original factorial range, which are represented by stars, and these are called axial points. So that's a classic central composite design for two factors. And you move the stars out far enough to get leverage, but if they're too far out, you can try to move them in. You could do a design that puts it into the center of each face. This, for two factors, that would form a full 3-level factorial, which is also a response surface method. The graph I see here shows that there's a big blow up in particle size at certain conditions. So there was a nice, flat, robust operating region for these two factors of time and phospholipid. Okay, so that's pretty interesting, isn't it? Now another design structure, which is the Box-Bentgen. If you don't want to go as far out and you want to just have 3 levels rather than 5 levels of each factor, the Box-Bentgen works pretty well. And this one, for 3 factors, it shows, a different location of the points at the midpoints of the edges. And this pharmaceutical developer, Carla, was able to apply RSM to screen down 8 factors in a 16-1. Well, first she screened down doing a 2-level. Then they took the vital 3 factors, 17-run Box-Bentgen, and were able to get increased yields. Wow, now this, I found a graph because it's got these mushrooms in it. All the other stuff around the outside of it, I'm not exactly sure what those are. But this guy, J. Peter Jones, designed an experiment to remove endocrine disruptors, or EDCs. And it's done with an enzyme preparation from this white root fungus, which I think looks like the picture there, but I'm not exactly sure. I made a note where the graphic came from, which was also related to EDCs. But bottom line is that by applying a full 3-level design, which I mentioned is a response surface method, I don't think it's too bad to do this with 2 factors. But with more than 2 factors, it generates too many combinations. I'd go to the Box-Bentgen. But they did some good things, right? A lot of good things. Okay, are you with me on that? Good things happening by the use of response surface methods. Okay, great. Another response surface method is applied for cell culture. You can see that the biotech is really building up here. As the years go by, I've got these listed by year, and you see a lot more biotech. In this case, optimizing cell culture bioproduction. And I'm not really going to have a chance to demo this, but if you have the software, check it out. But if you go in and try to do an 8-factor central composite design, it's going to be way too many combinations. But you can start, maybe I can show you that, and maybe it's easier to do it. It won't take me any longer. Because normally I wouldn't do a response surface method on so many factors, but maybe you've got one of these 96 well plates, and maybe you have a robot to pipette the plates. That would help. But even so, if you go to 8 factors, you'll see 282 runs. But that's with a full factorial core. If we cut the core into a high resolution half fraction, that cuts it down to 154. Use a quarter fraction, 90. And then you can use our optimal template for minimum run resolution 5 for the core, and that cuts it down to only 60. The other thing I wanted to mention is that with 8 factors, the rotatable that makes you equally precise predictions, equally distant from the center, that George Box and Wilson, his colleague, recommended back in 1951, that rotatable level, I don't think they ever thought anybody do 8 factors, is way, way out there. So Pat Whitcomb, our founder, and I worked with him before the company started in 1982 and incorporated in 1985, together as chemical engineers, came up with a way to take the 4th root of the number of factors and reduce the distance of the stars to a point where you still get advantage of some leverage from it, and you don't create crazy high variance inflation factors. And so this turns out to be a nice compromise. And so we just by default make it the 1.68 rather than the 2.4 to 2.48. So reducing the number of factors down, reducing the number of runs down rather, and then also reducing the distance of the star points out from the center. Those are some nice features that we have. Okay, this is another 3-level factorial on 3 factors, which is 27 runs. Remember, the Box-Behnken design only had 17 runs, so we probably could have done that. But this has got more power. And you can see this really cool sliver, which is a highly desirable sweet spot that they found in the lab, and it scaled up to production. So it was really, really successful to achieve their specs on strength, surface finishing, and accuracy for this unique 3D color printer. Very nice outcome. Now something completely different, froth flotation. We've done a lot of work in the copper industry. I actually did some work for my Bachelor of Chemical Engineering, mini project on liquid ion exchange reagents for a different process for copper purification called electrowinning. I have worked with copper mines that do the froth flotation up in Canada, and I taught a group of mining engineers one time up in Saskatchewan. So this was a 4-factor face-centered central composite, okay? So where the stars come into the face, and they were able to get really good models and then validate it. So with that, they were able to achieve, much better recovery, which was worth a lot of money. Oh, by the way, they were also purifying gold, or getting to a certain level of gold. They usually have to go to a smelter. Once they get the ground up particles through the froth flotation and they increase the copper content just a little bit, let's say from 2 to 6%, that's enough to go to smelters. And the operation in Canada actually sent them over to China, and I'm not sure if that's still going, to get the final smelting done. The application of DOE in this industry is very strong. And so it's really exciting to see this from Lauren Redden. This case study is interesting. We found a really nice sweet spot I have in the upper right corner. Time is not going to allow me to show this, but it was a 50-run Box-Behnken design. And it was done as part of a design for Six Sigma. It should be 6, it's designed for Six Sigma. And this was done at a well-known medical device company, and I had this all together to publish. And then the company decided that they didn't want to publish it because it was too important. They want to maintain confidentiality. So I took what they had, and with their permission, I disguised the some of the factors and levels and things like that. But it was very, very successful. They were able to double their medical device production rate with half the variation. So take a look at that if you get a chance. There'll be some information in the article itself, and you can get that from our case study site. You could also contact me on any of these, and I can send you a link. Okay, we'll finish off with mixture design. Now, this is an application of response surface methods, but within this special triangular space um, that maintains the total at a fixed amount, typically 100%. So you see here a classic design. This is actually done using a simplex centroid, but you could do it with a simplex lattice with the augmentation of these points for check blends here and this overall centroid. You could add those into a simplex lattice second degree, and it would be the same thing as a simplex centroid. And this was done with methyl ethyl ketone, toluene, and hexane, and different blends of these because they were trying to work out how to quickly dissolve a new compound that was related to ones that they already had. And so they had to kind of recalibrate, the blend of this, and they were able to do so very successfully, with this new organic chemical. So that's an example of mixture design, and it's unconstrained because they're going all the way to 100% for each of the three solvents. Now this one is a little bit different on this adhesive mixture design. Do you notice how the corner is cut off here? So this is another example of, in this case, a multi-component constraint, so that they don't go to the high level of this additive D, but they allow the rest of the space to be explored for their experiment. And doing this, they were able to have quite a success here, as you can read through. See that then we apply on optimal mixture design. Okay, again, these are all success stories, um, and hopefully they're providing inspiration for you or your clients that are working in certain industries. You can see that they're not the only ones. Other people in their area have done this. But I definitely would promote mixture designs if you're trying to optimize a recipe or formulation. Here's a fun one from Timothy Ebert, and actually was kind of a sideline of his. He's works in a different field, but he got interested in ceramics, and he knew about mixture design, so he developed this experiment for a ceramics class at a high school in Ohio. And they basically, each student could decide, which three stains they would work with. This student that we show in this picture here picked orange, yellow, and green. And then it kind of roughly fits out into a triangle, doesn't it? And I'm not really sure what color this is, but this looks like it's yellow to me, and this looks kind of green. But I'm not sure. Well, maybe this is the orange one. But basically, then you can see in this design space the different combinations and what that does to the color. So isn't that interesting? And so doing this was a great lesson in chemistry, stats, experimental design, and they also learned a lot about making glazes. So I think this is a really unique study that would be fun to try. Now back to biotech, we've got this work on animal cell technology, and so they were able to optimize the media, uh, and you can see that they get, a greater amount of viable cells, whatever this pharmaceutical product is, and then overall desirability is shown in the third plot. Another example of mixture design. Now this one, the triangle doesn't look very good. I had to make a note of that. The older version didn't always draw triangles equilaterally. Sometimes they'd be very narrow and sometimes they'd be very fat. We fixed that, but doesn't matter. You can see that they hit this sweet spot on luminance, as a function of these three pigments. So very successful application of mixture design. The red dots represent the different combinations of things, and you can see that they're cutting off corners here. So this would be an optimal design. Another mixture design, I'm just going to say go back and pull off the slide deck by going to the website at this stage rather than continuing to try to read through these. But you can see again a design that is areas cut off, and then you can see the population of points within the region that's feasible, and then you get this nice sweet spot. This is actually a mixture of three gases. They first, the interesting thing here is they first characterized process factors and got the process lined out. Then they turned their attention to the gases. And this is kind of a common combination of things. Maybe you optimize the formulation, then you develop the process, but you can also do combinations of the two, as I have one case study for combinations. Example on bread dough with 4 components. I like this one because they switch over to all natural ingredients. The has been unsuccessful doing this in the past, just using one component at a time, but they were able to get a really good tasting product for a bread dough. I'm not going to be able to build this design, but it's an example where they used a second degree quadratic simplex lattice mixture design, and they were able to maximize absorbency. Pharmaceutical manufacturing. Now, this one I bring up as a bad example because they used standard responsiveness methods. They were able to succeed with it, and RSM can be used when you have mixture ingredients, but I really prefer the mixture design. It does a better job of the stoichiometry of the chemistry, and it also is more efficient for the combinations of the blends than the RSM is. But RSM will work on mixtures as it was here. This was a cutting fluid, and the notable thing here is you see this trace plot, which I like to look at as kind of an overall view of the main component effects. And you can see that the emulsifier C has a big negative effect, and then B and C are A and B are positive going up from left to right. A combination of these three, they were able to get a more stable product. And then this is the combined one. I suggest you take a look at this and try it at home. Jessica Keel did a really great job, including a way to measure the breakage of the cookies with what's called a penny test. She would actually keep adding pennies till the cookie crumbled and use that as a measurement of how brittle it was. So this was a penny test on the right here. She looked at softness on a 5-point scale and taste on a 9-point scale. And what's cool about this is it's a combined mixture process using a special model called KCV that greatly reduced the number of runs. Thus, she was able to do it over a weekend. Well, mission accomplished. What do you guys think? Can you give me a thumbs up even though I went over the time limit? Okay, you're very kind. You're very kind. So please share your DOE successes. Get back to me at themarketstudies.com. As a lot of you know, I'm the author of this trilogy of books, and maybe something you send in to me might go into a future edition. You never know. If you have a need for further training, here's a slide that gives you some ideas on different classes for process, mixture, or you could do a private class, within your company. The contacts are there. Okay, thanks everybody. I really appreciate you bearing with me. As I suspected, I didn't quite make the 40-minute part, but there are 40 DOEs. So thanks again and have a great day.